In this video, I'm going to show you how to solve 8 different IV flow rate calculation questions, and we are starting right now. Hello, this is Dr. Dankwa, and if this is your first time here and you like to learn pharmaceutical calculations, tips, tricks, and strategies, then start by subscribing and clicking the bell so you don't miss anything. So if you need an in-depth tutorial and more examples on IV flow rate calculations, be sure to check out my other videos. I'll put links in the description and the cards should show up pretty shortly. So let's get right to it. This question says, if the infusion rate for an IV is 8 milliliters per hour and it is run for 4.5 hours, how many milliliters has the patient received? So to find the volume, what we need is the flow rate and the time component. From the question, the flow rate is given as 80 milliliters per hour, and the time is given as 4.5 hours. So we can multiply this by 4.5, which will be 4.5 hours. The hours cancel out, and you end up with 360 milliliters. This question says, a sterile solution request form is received for a large volume parenteral. The infusion rate is 125 milliliters per hour. 1 liter bags are requested for the next 24 hours. How many bags do you make? So here, the strategy will be to first determine the total volume that the patient would receive within the 24 hours, and then once we've determined that volume, we will use the volume of each bag to determine the number of bags that needs to be made. So to determine the volume, we need the flow rate and we need the time. The flow rate is given as 125 milliliters per hour, and the time is 24 hours. So the hours can cancel out, and the volume is 3,000 milliliters. So now that we know the volume, we can start off with the 3,000 milliliters, and from the question, each bag has a liter of sterile solution. Now, the units need to be consistent, so we need to convert the liters to milliliters, and the conversion factor is such that 1 liter contains 1,000 milliliters, and so the milliliters cancel out, the liters cancel out, and you end up with 3,000 times 1 bag times 1 divided by 1 times 1,000. So you multiply everything in the numerator, divide by everything in the denominator, and this ends up giving you 3 bags. This question says, how many drops per minute will a patient receive if an IV of 1,000 milliliters of 5% dextrose injection is run over 8 hours? The drip factor is 15 drops per milliliter. So here, the strategy would be to first find the flow rate in milliliters per hour, convert the hours to minutes, and multiply that result by the drip factor, also known as the calibration factor. So let's see how that works. To find the flow rate, we need the volume component. So the volume in the question is given as 1,000 milliliters. So we start off with the 1,000 milliliters. We need to divide this by the number of hours that the dextrose injection is run over, and that's 8 hours. So 1,000 ml divided by 8 hours. We need to convert the hours to minutes. So we use the conversion factor. 1 hour is 60 minutes. So now the hours cancel out, and then we multiply all of this by the drip factor. So that will be times 15 drops per milliliter. So we are using dimensional analysis. So the units in the denominator cancel out the units in the numerator. So the milliliters will cancel out. And now we need to multiply everything in the numerator and divide it by what is in the denominator. So we have 1,000 times 1 times 15 drops divided by 8 times 60 minutes. So the units are now drops per minute. And if we multiply everything in the top and divide by everything in the denominator, we end up with 31.25 drops per minute. Let's take a look at another question. This question says, you have a 500 milliliter bottle of an 8% drug. The rate of infusion is 5 grams per hour. A. What is the rate of infusion in milliliters per hour? B. How long will the bottle last? So let's start off with the solution to part A of the question. And the way we would approach this is to make use of the rate of infusion, which is a mass rate. So we start off with the 5 grams per hour. And now we need a conversion factor to get us to milliliters per hour. And that information comes from the percentage strength. So we have an 8% drug solution. And the 8% implies that you have 8 grams of drug in every 100 milliliter of solution. So now we can make use of that information and state that in every 100 milliliters of solution, you have 8 grams of drug. So now the grams cancel out. And since we are using dimensional analysis, we can essentially multiply all the terms in the numerator. So that will be 5 grams times 100 milliliters divided by 1 hour times 8. And that should be equal to 62.5 milliliters per hour. Let's now take a look at part B of the question. And here we are required to find how long the bottle will last. So the approach would be to take the 500 milliliter bottle and essentially divide that by the flow rate that we found in part A. But since we are using dimensional analysis, this is how it's going to look. We will start off with the 500 milliliter bottle, and we will make use of the flow rate information from part A, which tells us that in every hour, the patient is going to receive 62.5 milliliters. So now the milliliters can cancel out, and we essentially have 500 times 1 hour divided by 62.5. So you multiply everything in the numerator and divide by what is in the denominator. And so the answer is 8 hours. This question says, a physician orders a drug to be infused at 10 microgram per kilogram per minute. The patient weighs 70 kilograms. The total dose the patient is to receive is 21 milligrams. How long must the IV continue for the patient to receive this dose? So the first thing we need to do is to determine the rate for this particular patient. And so we will start off with the normalized mass rate, which is given as 10 microgram per kilogram per minute. And we multiply this normalized mass rate by the patient's weight. So that gives us 70 kilograms. The kilograms cancel out. And so now we have 10 microgram times 70 divided by minutes. And that gives 700 microgram per minute. Now that is the mass rate for this 70 kilogram patient. However, the dose to be given the patient is in milligrams, is 21 milligrams. So we want to convert the micrograms to milligrams to make the next step easier. So we make use of the conversion factor, which states that 1,000 microgram make up 1 milligram. So the micrograms cancel out, and that is equal to 0.7 milligrams per minute. So now we can determine the time by dividing the total dose that the patient receives, which is 21 milligrams, by the mass rate determined in the earlier step. So now, since we are using dimensional analysis, we'll start off with the 21 milligrams, and then the mass rate is 0.7 milligrams per minute, which means that in 1 minute, the patient would receive 0.7 milligrams of drug. So the milligrams cancel out, and that implies you have 21 times 1 minute divided by 0.7, and that is equal to 30 minutes. This question says, an order for a patient with a 3-liter daily IV fluid limit calls for 3 liters of D5W with a 100 milliliter IVPB antibiotic to be run in alone over a 1-hour period, administered every 6 hours. The administration set is calibrated to deliver 10 drops per milliliter. Calculate A, the flow rate of the IVPB antibiotic, B, the total flow time for the IV antibiotic, C, the total volume of the IV antibiotic, D, the total flow time for the D5W, E, the total volume for the D5W, and F, the flow time for the D5W. So the question has 6 parts. The first 3 have to do with the IVPB, which is your IV piggyback. And then the last 3 from D to F have to do with the large volume parenteral, which is your D5W. So we can start off by solving part A. And A is asking for the flow rate of the IVPB antibiotic. So the strategy would be to take the volume of the IVPB, which is 100 milliliter, divide that by how long you are running it, which is 1 hour, convert the hours to minutes, and multiply that result by the drip factor, which is 10 drops per milliliter. And so what that would look like is you have 100 milliliters, which is the volume of the IVPB, divide that by how long you are running it, which is going to be 1 hour. We convert the hours to minutes. 1 hour is 60 minutes, and we multiply this result by the drip factor, which is 10 drops per milliliter. So the milliliters cancel out, the hour cancels out, and now you're in drops per minute. So since we are using dimensional analysis, we are going to multiply everything in the numerator. So that'll be 100 times 1 times 10 drops divided by everything in the denominator. So that'll be 1 times 60 minutes. Now that should be equal to 16.67 drops per minute, or approximately 17 drops per minute. So we can now solve part B of the question, which is asking for the total flow time of the antibiotic. And the way we find the total flow time is to multiply the number of times that you are running the IVPB by how long you run each bag. And so what that would look like is you have a total time of 24 hours. You run the IVPB every 6 hours. And each bag is run for 1 hour. And so the total flow time will be 4 hours. So we can now go ahead and solve part C of the question, which is asking for the total volume of the antibiotic. And the way you find the total volume is to multiply the number of times that you run the IVPB by the volume of each bag. So what that would look like is you have a total time of 24 hours, and every 6 hours you run one IVPB, one bag. So this ratio gives us the number of times that you would run the bag, and the volume of each bag is given as 100 milliliters. So the hours cancel out, and your total volume will be 400 milliliters. We can now solve part D of the question, which is asking for the total flow time for the D5W. And the way we would approach that is to take the 24 hours, which is how many hours you have in one day, and subtract from that the total flow time of the antibiotic, which is given in part B to be 4 hours. So that will end up giving us 20 hours. So we can now go ahead and solve part E of the question, which is asking for the total volume for the D5W. And the way we would approach this is to take the patient's daily IV fluid limit, which is 3 liters, and subtract from that the total volume of the antibiotic, which is 400 milliliters. Now, for the units to be consistent, we first need to convert the 3 liters to milliliters. So 3 liters multiplied by the conversion factor, 1 liter is 1,000 milliliters. The liters cancel out, and that gives 3,000 milliliters. So from this 3,000 milliliters, we will subtract the total volume of the antibiotic, which is 400 milliliters, and that should be equal to 2,600 milliliters. We can now solve part F of the question, which is asking for the flow rate for the D5W. Now, the way we will do that is to take the total volume for the D5W, which we calculated in part E to be equal to 2,600 milliliters, divide that by the total flow time for the D5W, which we calculated in part D to be equal to the 20 hours, and then convert the hours to minutes and multiply that result by the drip factor. So what that will look like is we have 2,600 milliliters divided by 20 hours. We convert the hours to minutes. In 1 hour, you have 60 minutes. The hours cancel out, and we multiply this result by the drip factor, also known as the calibration factor, which is 10 drops per milliliter. So the milliliter also cancels out, and now you're in drops per minute. So since this is dimensional analysis, we will multiply everything in the numerator. So you have 2,600 times 1 times 10 drops, and divide that by everything in the denominator, which would be 20 times 60 minutes. And that is equal to 21.67 drops per minute, which is approximately 22 drops per minute. This question says a 250 milliliter bag of D5W is to be infused at 40 drops per minute. The IV set drop factor is 60 drops per milliliter. The IV is started at 6 a.m. When will the next bag be needed? So the way we want to approach this question is to first calculate how long it's going to take to infuse the 250 milliliter bag of D5W. Now, once we've calculated that, we can then determine when the next bag will be needed. So to do that, we need to identify from the question any parameter that has a time component. and we see that the flow rate, which is 40 drops per minute, has a time element being the minutes. So the first thing we want to do is to start off with the flow rate, 40 drops per minute, and what that implies is that in every single minute, you are able to give 40 drops. Now we are using dimensional analysis, so we can go ahead and multiply this ratio by the drop factor, which is 60 drops per milliliter. Now at this point, the drops can cancel out, and we are now left with minutes per milliliter. So we can go ahead and multiply this by the volume of the bag, which is 250 milliliters. So now the milliliters cancel out. So we are using dimensional analysis, so we can go ahead and multiply all the terms in the numerator. So that will be 1 minute times 60 times 250 divided by 40. And that is equal to 375 minutes. So to make the calculation easier, we can go ahead and convert the minutes to hours, which would imply that we have 375 minutes. We convert that to hours. So the conversion factor is 1 hour contains 60 minutes. The minutes cancel out, and that is equal to 6.25 hours. So the 0.25 is not 25 minutes, but rather is a quarter of an hour. So just to be clear, we can go ahead and convert the 0.25 hours to minutes. So that would imply that you have 0.25 hours. We convert that to minutes. 1 hour is equivalent to 60 minutes. The hours cancel out. That means you have 15 minutes. And so this implies that you're actually going to be infusing the 250 milliliter bag of D5W for 6 hours and 15 minutes. So if you started the IV at 6 a.m., then 6 hours later will be 12 noon, and 15 minutes later will be 12:15. So that would imply that the next bag will be needed at 12:15 p.m. This question says a medication is ordered by the physician 2 grams in 250 milliliter normal saline to be administered by continuous IV around the clock for 24 hours. The rate of infusion is 100 milliliters per hour. If the first bag is started at 0800, how many bags in total will be needed? And so the strategy here would be to first determine the volume administered in 24 hours. And the way you do that is to use the rate of infusion, which is 100 milliliters per hour, multiply that by the total time, which is 24 hours, and that will give the volume administered. Once we found this volume, we will divide that by the volume of each bag to give the number of bags. So let's see how that looks like. So we can start with the rate of infusion, which is 100 milliliters per hour. We multiply this ratio by the time, which is 24 hours, and make use of the information provided, which states that each bag has 250 milliliters. So now the milliliters can cancel out, the hours cancel out, and what we can do next, since this is dimension analysis, is to multiply all the terms in the numerator. So we have 100 times 24 times 1 bag, and divide that by all the terms in the denominator. So divided by 250. So this will be equal to 9.6 bags, which is approximately 10 bags. So I hope you found this video tutorial useful. If you did, be sure to like it and share it. And if you have any questions, leave them in the comments and I'll get to them as soon as I see them. If you would like to learn more pharmaceutical calculations, tips, tricks, and strategies, then start by subscribing and clicking the bell so you don't miss anything. Thank you so much for watching, and I'll see you in the next video.